All right, I'm getting the screen turned on. Give me a second. There we go. Let's get started. Can you believe that this is lecture 30? Can you believe that?
I'm gonna say I can.
What's that?
I said yeah, I can.
You can. I don't know if I should take that as a compliment or an insult.
Oh, I've been here for all of them, so I can believe it. Yeah.
Okay. Now I'm definitely taking it as a... That's okay. It's okay. All right. Just a heads up, my plan is to grade and to give you your submittal 1 back on Monday because submittal 2 requires MASTAN. So what I want is I want everybody to do the MASTAN assignment, and then when you turn it in on Monday, I'll give the submittal 2 assignment to you right then and there. Obviously, just got exam 2 on Monday. How did everybody think it went? Everybody, okay. Was it, a nightmare? Wasn't that bad, was it?
It wasn't very turbulent.
Was it? Oh my goodness. Okay. Oh my. The fluids puns continue. Okay. I'm giving you homework 7 today, but it is not due Friday. It is due on Monday. Okay. Homework 7 is the software assignment. And honestly, the reason I'm having it due on Monday is just because I'm doing it all in one assignment. It's not as if, ooh, he's giving us an assignment, it's a lot of work. These software analyses are actually pretty quick. You just have to, screenshot it and write it up and all that, but it's really not that bad. It's not a lot of work. I think homework 6-2 was definitely more work than this one. So, okay, did everybody get the QR code?
Oh, okay.
Everybody get the QR code?
Yes.
Okay. All right. All right, everybody. I know we're in fluids land, but let's go to the land of structures for 50 minutes. Before we open up MASTAN, which you all can load it up on your machines, but I want to talk a little bit about MASTAN, about how it works, and what sort of the motivation is. One of the things that we haven't talked about yet is indeterminate structures. We haven't talked about it yet, but I want to use today's lecture as a little bit of a breakdown into how indeterminate analysis works. Okay, but let's talk about MASTAN. So MASTAN first. So MASTAN is the structural analysis software package we're going to use this semester. I picked MASTAN for a couple of reasons. It's easy. MASTAN is not a difficult package to use. It's a really, really straightforward software package. It's also free. It is 100% free. I want to give a shout out to Professor Ron Zemian at Bucknell, who's made MASTAN free for anybody to use. It's Mac friendly, it's Windows friendly, so it's really, really nice package in that regard. It can do quite a bit. We're only going to be doing linear analysis. We're only going to be doing 2D in here, but it can do 3D. It can do nonlinear. It can do buckling. It can do a lot of really, really good stuff. And what I'll say is it can also do determinant analysis and indeterminate analysis because it uses a process called matrix stiffness analysis. In fact, MASTAN stands for matrix stiffness analysis. MASTAN, that's where it comes from. There are some limits to MASTAN, though, that I want to mention right off the bat. Number one, it cannot handle triangular loads or trapezoidal loads. So that's something you would have to do on your own. And it cannot handle loads that move. It cannot handle moving loads. Moving loads is going to be the topic of discussion next week, so just wanted to mention that. But if you wanted to get pretty adventurous and you wanted to flex your MATLAB skills, the source code is available, so you could do that as well. I get the feeling you all are like, let's move on. Okay. We have not at all discussed indeterminate analysis. Now, let's talk about indeterminate structures, though. What we have done is we have been able to classify determinacy. So I have here this structure drawn on the board. This structure is going to show up on the slides here in a little bit. But how would we determine whether or not this structure is indeterminate or not? Do y'all remember how to do that? We calculate the I sub E value. Do y'all remember that? So what is I sub E for this problem up here? We have a pin support, a roller, and a roller. So we have 2, 3, 4 reactions. We have 3 equations of equilibrium. So this structure is indeterminate. It's indeterminate to the first degree, right? There's one too many unknowns. Okay. Keep that in mind. Okay. Now, first off, I should have a little bit of a side as to why would we even use an indeterminate structure to begin with. Indeterminate structures are, by their very nature, more involved when it comes to analysis. So if you're going to have to do all this extra work to analyze the structure, why even use them? Okay? Well, there are 2 really key reasons why you would use an indeterminate structure. The first is that indeterminate structures have a resulting internal response that's less than their determinate counterparts. So for example, this is a simply supported beam with a uniformly distributed load. If I look at the midspan deflection, I can calculate that as 5 WL to the 4th over 384 EI. If I fix both ends, instead of 5 WL to the 4th over 384 EI, it's 1 WL to the 4th over 384 EI. So what I'm saying is this structure has a maximum displacement that's just 20% of this one. So I could use a smaller beam. Saves money, right? What about the moments? This maximum moment is WL squared over 8. The maximum moment over here, WL squared over 12 or WL squared over 24. So less bending moments, less deflections, okay? I skipped ahead. But the other advantage is that they contain redundancy. So if I have a bridge that has a pier in the middle, okay, like this one, okay, that's indeterminate. If I were to stick a hinge right here, that would make the structure determinate, and I can solve it like I've been doing this whole semester. But if that central pier were to fail, that bridge is in the river, okay? But if I leave that hinge out and I keep the structure indeterminate, okay, then if that pier fails, at least the structure is statically stable, okay? So adding indeterminacy adds redundancy to the structure in the event of certain elemental failures, okay? So why would you use indeterminate structure? Well, you can use smaller elements and they have redundancy when they fail. That's a pretty good reason to use an indeterminate structure if all we're worried about is a little bit extra math, okay? Does that make sense? Now, that doesn't answer our question in CE 312 as to how to analyze the structure with indeterminacy. So let's take a look at this problem. Okay, this is the problem that I have drawn here on the board. Okay, this is this problem right here. Okay, so it's indeterminate to the first degree. Okay, and what I mean by that is there are 4 reactions, 1, 2, 3, 4, and there are 3 equations of equilibrium. Now, we could easily solve for one of those reactions right now. There are, though, horizontal forces on the structure, so we know this horizontal reaction is 0. That's easy. But we have 3 vertical reactions, and we really only have 2 independent, unique equations of equilibrium to relate them. So we have one too many unknowns. So how do we handle this? Okay? The way that we handle this is we have to use the relationship between forces and deformations, and that is the key to any indeterminate analysis. So we weren't really able to have an intelligent discussion about indeterminate analysis until we had already discussed deflections. Okay? When you apply load to a structure, it deforms. Okay? If you understand that relationship, then you can analyze an indeterminate structure. So let me ask you a question. What is the vertical deflection at point B on this problem? What's the vertical up and down displacement at point B? It's not a trick question. It's 0. Point B is a support. The beam is not displacing at point B. Like if I were to draw what this beam looks like when it deforms, it probably looks something like this. Right? Would you agree it's going to kind of flex and bend something like this? But at point B, it doesn't displace at all, right? So you asked me, how do I solve for that additional equation, or how do I solve for that additional unknown? Well, now I've got 4 equations that I can use. The sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, the sum of moments equals 0, and deflection at B equals 0. That is my that is a potential 4th equation. So how does that work? Okay, so this is my original problem. Okay, so I'm going to go through a very basic method for indeterminate analysis. Okay, So the first thing that we could do is okay, so here's a copy of the structure. What I'm going to do is I'm going to take this roller and I'm going to get rid of it. I'm just going to delete that roller from the structure. Okay? So it's gone. Is this problem one that you all can do in here? Could you analyze this structure? Well, I mean, you should be able to. We just have tests on it, right? This is well within the realm of possibility. Okay? So what we'll do is we'll remove that roller, okay, and we'll allow the beam to deform. Okay? So I'm going to call this the primary structure. Okay? And so this is going to be problem 1. Okay? And problem 1, what I'm going to ask you is, what is the deflection at B? Okay, so how do you solve for that displacement? Well, you take this problem, you've got a real structure, you do a virtual structure, integrate little m big M over EI dx, sum all that up, okay? I'm hoping that you all can do that, right? Okay? So I propose that for this problem, you all can check me, this is a problem that's well within your ability to do. I propose that delta B ends up being 4.22 inches downward. Is that a reasonable value? Everybody with me on that? Okay, so that's problem 1. What's problem 2? Well, problem 2, I'm going to call this the redundant structure. Here's how problem 2 works. Okay, so if I kick that roller off, would you agree that this deflects 4.22 inches downward? Everybody agree with that? So what if I then ask the question, let's take the structure, no loads on it, no loads, just blank structure, and let's put an upward force right here. Let's call that, I don't know, By. Here's my structure. Let's just look at this problem in a vacuum by itself. Would you agree that this structure is going to flex upward something like that? Does that make sense? Maybe what we'll ask is how much, or getting ahead of myself, how much does By need to be to push the beam upward? .22 inches. That's a problem that you all could probably do as well, right? Maybe a little bit more algebra, but it's well within, I mean, this is a problem as well. This is definitely a problem you all could do. So what we're talking about, this is what's called the method of consistent deformations, okay? So what we do is we remove from the structure one of the extra supports. We analyze that structure, figure out how much the structure deforms with that support gone in that location. Then we do a separate analysis and ask, well, how much does that need to push up so that the net displacement is 0, okay? And you can solve that and you end up finding that that force, By, is 63.75 kips, okay? Once you have that, you can go back to this original problem and say, well, let's just say that that reaction is 63.75 kips, and now it becomes a regular problem. Solve for reactions, draw a shear diagram, draw a moment diagram, the problem's done, okay? That is the method of consistent deformations, and in a nutshell, that is the most bare bones basic indeterminate analysis method, but it'll work for pretty much any problem that you would ever do, okay? So you could get this reaction, that reaction, draw a shear diagram, draw a moment diagram, etc. Okay, that's the most basic indeterminate analysis method I can show you. Everybody with me so far? Now, a question for you is, why don't we, well, do we do this very often in practice? No, okay? And the reason why is because it requires us to select a redundant. Now, everybody in this room is a human being, and we can look at the structure and we can say, it kind of makes sense to select B as the redundant, so we'll deform, push up, etc. But there's actually nothing theoretically wrong with choosing C as the redundant or A as the redundant. I could actually do the problem the same way. It would completely change the individual calculations. It would change the, the individual steps of the process. But at the end, theoretically, it would work. Why don't we do that in practice? Well, the reason we don't do it in practice is because it makes the method difficult to standardize. And I guess more relevant to today's discussion, it makes the method more difficult to write a computer program for. Okay? What we want to do is we want to create a method that we can just plug a structure in, click a button, and it gives us an answer. Okay? And with this problem, let's also be clear, this problem had one redundant. The I value was 1. What if the I value was 47? How would you choose the redundants and how would you systematize the process? It would be a nightmare. Instead, we're going to flip to an entirely different type of analysis. So what I have here on the board is what we call a flexibility approach. And a flexibility approach is where you're ultimately solving for unknown reactions. Like you use this indeterminate approach to solve for unknown reactions. That's a flexibility approach. A stiffness approach is where you're flipping the script and solving for unknown deflections. Okay? And it is much more easy to program and standardize stiffness-based approaches. We're going to learn a little bit about that near the end of the semester. Okay? So the method that we use, and the most ubiquitous indeterminate analysis method that we use in application, is what's called matrix stiffness analysis. Okay? And so I want to give you a brief insight into how it works. Later on in the semester, we'll dig into it with a little bit more detail. Okay? So I want to go back to Engineering 216, and I want to have a very basic discussion about matrix analysis, or about an axially loaded bar. And I'm going to use this basic discussion about an axially loaded bar to break down matrix analysis. So let's say I have a bar, I yank on it with some load F, it stretches some amount delta. Okay? You all should know that we can calculate that amount of stretch as delta equals FL over EA. I'm assuming by now everybody's comfortable with that, right? Okay? So I'm going to rewrite that expression a little bit. I'm going to flip and multiply, and I'm going to say that we could write F as delta times this term right here, this EA over L. Or another way I could write it is F equals K delta, where K is what I'm calling the stiffness. Do you all remember it's probably Physics 211 where you had spring problems? Y'all remember that? And there was a spring, and that spring had a spring constant. It was like a spring stiffness K. Did y'all do that in physics? So it's the same idea, okay? That I can, for a given element in a structure, I can replace that element, or I can define a stiffness term for that element, okay? Now I'm looking at a single bar, okay? But I propose that this truss is just a bunch of bars, okay? And so instead of looking at it like this big old structure, I want to look at it as an assemblage of bars that are axially loaded. And I'm using that term assembly very, very carefully because we'll talk about that later, how we assemble structures and whatnot. So instead of saying the force equals the stiffness times the displacement, instead I'm going to say, well, what about a force matrix equals a stiffness matrix times a displacement matrix? And so what we'll do is we'll essentially form a model that represents the entire structure and solve for it in one fell swoop. Okay? The reason why that's advantageous is because these things solve these problems very, very efficiently. They love doing matrix analysis, and they can do it like that. Okay? So how does matrix analysis work? Here's how it works. I'm going to throw some terms at you that I'll be using over the next few days, so I want to make sure you're clear about that. So the first thing that we do is what's called pre-process. And pre-process is just a fancy term for creating our model. So for a given structure, we're talking about creating the geometry. So that's the joints, the members, the boundary conditions, etc. We're going to create the loads on the structure. We're going to apply the stiffness to each member, what material it's made out of, how big the sections are, etc. Okay? Once we do that, we click a little button called Go, and it just solves the whole thing. How does it do it? Well, the first thing it does is it takes that spring value for each member, and it comes up with what's called a spring matrix, or we call it a stiffness matrix, a K matrix. So we get a stiffness matrix for each member, and we assemble them into a big old K matrix for the whole system. We do the same thing with the forces, because we define the forces that are on the model. So we have our stiffnesses, we have our forces, we then just solve for our displacements. It's just a simultaneous system of equations. Solve for our displacements, take those displacements, plug them back in onto a member-by-member basis, get the reactions, get the forces in each element, and then we post-process, which post-process is just visualizing the answer, looking at the support reactions, looking at the internal member forces, looking at the deflected shape, etc. We just click a button, does the whole thing, okay? We'll go through this process in a little bit more detail near the end of the semester. Now, what we're going to do in here are some really, really simple structures, but you can do finite element analysis for some really out there stuff. This was some finite element models that I created in my research group. We were looking at deformations in bridge girders that are under truck loads. So this was the underside of a bridge as the truck was going over the bridge. This is a slope stability finite element analysis, looking at the slope failure surface and whatnot. You can even do thermal analysis and stuff. You can do some really crazy stuff with matrix analysis. Okay. Any questions? All right. So let's talk about MASTAN. Okay. I've got a handout that I'm going to pass out, and it'll be sort of a guided exercise that we all do together. But before I pass that out, I want to make sure that there's some ground rules on how MASTAN operates. This is really important because this is the type of stuff that you can make a mistake on when you're running MASTAN. Okay, so first off, if you run MASTAN, if you open it, it looks like this. It's a pretty basic interface. Okay, so the first thing that you should notice is you've got the menus up here. Okay, and so what you do is you'll open the menu. It'll contain all the necessary commands to build a model or to execute a model. So in the menu, you will call a command, and when you call that command, all the entry, the data entry for that command will be down here. So you just call a command up here, and then enter in all your values down here. You enter in all your values, click the little apply button, everything will get executed. Okay? There are several menus. I'm not going to spend a whole lot of time talking about like the file menu or the view menu, but there are a couple things maybe worth mentioning. In the file menu, there's an option to export a photo for a report. So this is great for like your homework assignments, because I'm going to ask you to do a homework where you're generating a model, and you can literally just export the photo right here. Creating a report is also kind of nice, because you can say, give me all the joint displacements, give me all the member forces, and it'll do it. View menu, you probably won't use all that much, but this is if you want to rotate or zoom or what have you. Okay, units. Let's talk about units. Okay, whenever you're writing a structural analysis package, there are two ways to handle units. The first is to build a program that will convert the units for you. I mean, that is convenient. The problem is that if you're using a unit system that's slightly different, your hands are shackled. Okay. The other way is to just not incorporate a unit system at all and allow the user to use the units that they see fit. This is how MASTAN works. I mean, there are some programs, I mean, like Abacus, they make space shuttles with Abacus, and this is what Abacus does. So this is, there's definitely, you know, prerequisite for that. So as the analyst, you need to adopt a consistent unit. Okay, so what I'm proposing that we do in here is we do our forces in kips, and we do our member dimensions in inches. Now, the nice thing about MASTAN is that when you're entering the coordinates, you actually do the calculation inside the data entry, so it makes it a little easier. You don't have to actually calculate values on the side, but you do need to multiply your member lengths by inches. You need to divide your distributed loads by 12. You need to multiply your moments by 12, etc. And that's why we do this, so that we have practice for it. Just wanted to make sure that was clear. Okay. In terms of sign conventions, okay, and terminology. So first off, terminology, I am going to use the term joint and the term node interchangeably. I'm going to use the term member and the term element interchangeably. They mean the same thing respectively, okay? Units, again, kips and inches. I'm also going to want to make sure that we're consistent in our sign conventions. So what do I mean there, okay? Oh, that was... for the x direction, we're going to consider forces... for the x direction, we're going to consider forces to the right being positive. So, for example, if we do a structural analysis and we get a deflection in the x direction that's negative, that means it's to the left. So MASTAN's already adopting rightward forces and displacements and positive, y direction upward forces and displacements are positive. For rotations, it's assuming counterclockwise moments. Counterclockwise rotations are positive. And for axial forces, tension is positive. Okay? And the reason why is, like, when we do a matrix style analysis, we have to write equations of equilibrium over and over again. So we have to have some sort of consistency in our sign convention and whatnot. Also, we're going to keep things in 2D. We could expand all this to 3D, but we're not going to do that in here. In most civil engineering applications, you try and stick it to 2D if you can. Okay. Building a model and running a model takes 5 steps. So the first thing you're going to do is you're going to define the geometry, okay? You're going to define the properties and attach those to the material or to the model. You're going to define what are called the conditions. And I'm using the terms that MASTAN is reading. So if you look at the menu on the very top, it literally should have geometry, properties, conditions, etc. You'll then analyze the structure and then post-process the results. So the model or the example that I'm going to do with you here in a bit is this example. And if you look at the slides, you'll see that I've got these little buttons here on the slides, so you'll be able to follow along with me. You'll know what step I'm on as we do it. So let me go ahead and pass this around. So 1, 2, 3, 4, 5, 6, 7. If you have any extras, I guess just pass them back to the row behind you. And I've got extras up here if we need. Okay. So hopefully everybody here has MASTAN open. This is the problem that we're going to analyze. Notice that we've got loads in different directions. We've got members with different properties, etc. So the first thing that you need to do is open up your MASTAN. Once you've opened MASTAN, oh, you need one more? Okay. So the first thing that you want to do is you want to open it and then go File, Save As, and save the problem that you're working on. I think I'm calling it EX30.MAT. EX30 just because we're in Lecture 30 right now. I will say that this is a MATLAB-based program, so you do need to follow like MATLAB conventions when you're naming files. So no starting with symbols, whatnot, no spaces, things like that. Okay. And again, like I'm fully fine with you all working a little bit on your own, but I'll say a few things while we're starting. So in terms of terminology, so I said I was going to use the term node and element interchangeably. A node is where the software is going to directly compute deformations. So the way that matrix analysis works, you directly compute the deformations at the nodes, and then everywhere else it's interpolated. So as an analyst, what you want to do is place nodes at all the support locations, anywhere there's a hinge, anywhere there's a truss joint, anywhere there's a point load. And then what I say is if you have any other points of interest, go ahead and put a node there. Elements are the regions, so like what matrix analysis does is it breaks down the model into these discrete regions that we call elements. It writes a stiffness matrix for that element and then assembles them. The types of analyses that we're going to do, one element per member is completely fine, but if you're doing a nonlinear analysis, Like for example, this beam, like right here, if we look at this redundant structure, I would model it with an element from here to here and an element from here to here. But if this was a nonlinear analysis or something, I might have 10 elements and 10 elements, because the more elements that you use, it can adjust your accuracy. But that's only in nonlinear land. Okay. Whenever you're defining your geometry in MASTAN, the geometry is relative. Okay. So for example, if I wanted to create these two joints, and these two joints need to be 100 inches apart along the x-axis. I could put this one at 0, 0, and this one at 100, 0. I could put this one at 0, or 0, 36, and this is at 136. I could put this one at 25, 0, this one at 100, 0. It doesn't matter as long as you use a consistent origin. So if you look at the very first page on the model, on the handout that I provided, I'm assuming the origin is at node 1. So the coordinates of node 1 are going to be 0, 0, and what have you. All right, so you can see, oh yeah, right here. So this is the y-axis, this is the x-axis. I'm going to treat that as a 0, 0. One thing I guess I should mention, nodes are numbered, not lettered. So they're not going to be in A, in B, in C. It's going to be in 1, in 2, in 3, in 4, in 5, etc. Okay? So, first thing I want you to do is create your 5 nodes. Notice how, like, when you're doing the data entry, you do not have to type the number 144. You can do 12 asterisk 12, and it will do the calculation. So you can have MASTAN do the calculation for you. That's completely fine. You do have to enter a z-coordinate for those, so the z-coordinate is 0 for all of them. But you should be able to create your 5 node coordinates. Again, just go to geometry, define node, and then go through that. So I'm going to give everybody a sec on that, and before I jump on to the next thing. Go back here, see how everybody's doing in their nodal creation. And again, you don't have to type, for example, the number 144. You can do 12 times 12, and it will work, okay? You can do the math inside MASTAN. Okay. After you create each node, what it'll do is it should say, like if you do the first node, you'll do like 0, 0, hit apply, and you should get a little message on the right that says like success, node 1 defined. And so you'll do that like 4 or 5 times. The other thing I'll say is that if you need to delete a node, you can delete a node and restart, excuse me. So I see you've got ones you probably need to redo. So so what you want to do, okay, so let's look at this. So for you, let's see, so N4 and N5, what I'm going to do is I'm going to cancel this. I'm going to try geometry, and we're going to move nodes. So we're going to move this node and this node. And how much are we going to move it? We're going to move up the Y 8 times 12. Wait, oh, I need to.
Oh,
yeah.
and you click this?
Yeah.
Okay.
MASTAN does give you a number of different means of correcting your mistakes. Okay? So after you define the nodes, the interface should look something like this. I've inverted the colors here on the slide, so I mean you're seeing like a black interface with white text and whatnot. I've inverted it here on the slide, but it should look something about like that. Then you're going to define the element. Defining the elements is pretty easy because all you have to do is draw a line. One thing I strongly suggest in your modeling practice when you create joints, or sorry, when you create elements or members, is to draw the line from the lower numbered node to the higher numbered node. So, like for example, this member right here, this one, create it from N2 to N4. Don't do it the other way around. It won't really matter on this problem, but for beams and frames, it really does matter. So I just get into a good habit of going from lower number node to higher number node. So when it's all said and done, this is what your structure should look like after creating the geometry. It should have your 5 nodes, all of your members, and the members should be rendered with this sort of dash dot, dash dot, dash dot line. So the way that MASTAN works is that it will render the members as dash dot because they have no property definitions. Once you apply the materials and the sections, the lines will become solid. So it's a really easy way for you to see that all the properties are defined. All right, everybody got that? All right, anybody have any questions about step 1? Step 1 is the geometry, creating the geometry. Anybody have any issues? And again, if you're chugging ahead, that is okay. I am fine with that. Okay. All right, so a couple other points I'll mention on member orientation. When you're creating members, again, it doesn't really matter about there's this thing called element orientation. So element orientation is if you draw the element from node 1 to node 2, but the element itself is rotated. That doesn't matter for beam or for trusses, but it does matter for beams and frames. Won't matter today. We're also gonna, on Friday, we're gonna use the geometry menu to define connections, because connections are how MASTAN models hinges and whatnot. So, okay. All right, so we're done with geometry, and now we're going to move down to properties. So in properties, what you're going to do is you're going to create 2 things. You're going to create sections, and you're going to create materials, okay? Now, sections and materials are where, essentially, like if we look at this problem here on the board, the materials where we get the E value, the sections where we get the I value, okay? Now, there's 2 ways to create a section. You can create one from scratch, which is what we'll do on Friday. Today, we're going to use the library. And the nice thing about the library is that all these sections are already in there. So, for example, what we're going to do for, let's say, one of the truss members that's, I think it's horizontal, one of the truss members that's horizontal is a W12 by 22. What you'll do is you'll go to Properties and Define Section. And then instead of entering in all those numbers at the bottom for a W12 by 22, just click this little database button and you'll get a big old list. Just find the W12 by 22 and all the sections are built into MASTAN. It's almost like I thought about that when I was devising your class project, and I would devise a project where you had to use sections that were already inside MASTAN. It's crazy I would consider something like that. It's like I was trying to make it easy on you or something. You're welcome. Whenever you're assigning sections, you have to create the sections, then you need to attach them. So you're going to attach the sections, you know, like this, this, and this, and then create another section, attach it to this, 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 and this. The line rendering will change. It'll go from dashed dotted to dashed. And that rendering says, okay, there's a section defined, but there's no material defined. Now the material, oh, I went ahead one too many. Let me go back here. So for materials, you do have to create that yourself. So we're going to define a material called steel. We're going to define a material that has a Young's modulus of 29,000. Notice how we're retaining kips and inches in everything. We put our nodal coordinates in inches. We're putting our Young's modulus in KSI. The section database is already in inches, so we're maintaining kips and we're maintaining inches. Okay? So what we'll do is we'll create a single material and we'll just attach it to everything. And when it's all said and done, you should have solid line elements for the entire structure. I'll give everybody a second on that. Yes?
So, I went to properties and define sections, and I accidentally done it twice.
That's okay.
So properties, remove section.
If you want, you can just remove them all.
So hold on, let's see. Yeah, we'll just remove section 2. And then now we'll geometry, or sorry, properties, define a section. See where it says section 2? So now you've already deleted the one, says it 26, or it says 12 by 16? So now we'll just apply to section 2 define. So you just delete it and start over.
Your modeling file is a little difficult to break completely, and you can always just delete something and restart, so.
Would you define section 2? With the W16?
How's everybody doing?
Dr. Mike,
Yes.
I got to the end of the materials part, and these two still look a little weird.
Properties, attached material, select all, apply, view. Okay, I'm not sure that you attached your section. Did you attach the attached section to? Oh, you created a unique section for each one. You only need to create. Yeah. So let's. Yeah. So okay, let's talk about that. Let's clarify that a bit. So the way that sections work. Okay, everybody, eyes up here.
I see.
Okay, eyes up here, everybody. Let's just make sure it's clear. Okay, how many elements are in this truss? There are 7 elements, right? You do not need 7 sections, okay? I want you to think of sections like buckets of paint, okay? So we have the W12 by 22, which is a blue bucket of paint, and the W12 by 16, which is a red bucket of paint. And what I'm saying is 3 of these members are blue, 4 of them are red. So you only need 2 sections, okay? Does that make sense? So you create section 1, apply it to 3 members. Create section 2, apply it to 4 members. Okay? Does that make sense? That's okay. I mean, will the model break if you created 7 sections and applied section 1 to member 1, section 2 to member 2, etc.? No, it won't. So it's just not as efficient. So it'll still work. How's everybody doing? Doing good? Okay. I'm going to skip ahead just a little bit. So we're going to get into now our conditions. So this is the last thing that we have to create before we actually start running the model. And so we're looking at 2 different types of conditions. We're looking at fixities and then the loads. So fixities are our boundary conditions, the pin support, the roller support, etc. Okay? So once we do the fixities first, then we'll do the applied loads. For defining fixities, all you have to do is conditions, define fixity, and apply accordingly. Now, the way that you have to do your fixities, I'm gonna show you how this works here on the next slide. So my advice to you for defining fixities is to do it 1 node at a time. So node number 1 is a pin support. So it has an X and Y fixity. So what I would do is define your fixity for node 1, do X and Y, hit apply, and then hit the clear button, do here, and make sure that only the Y is created. One of the most common mistakes with fixities is that you end up applying too many, but it's okay. You can always just completely exit out of the fixity command and just recreate them. Just make sure that you're going Y for node 3 because it's a roller, X and Y for node 1 because it's a pin. Alright, I feel like most of you are making this work. Okay. So, everybody good up here? Alright. For your loads are pretty straightforward. You just do it on a node by node basis. The big thing that you gotta make sure with when you're defining your nodal forces is that your sign convention is handled correctly. So for example, when you look at node number 4, there's a vertical load, but it's acting downward, so you need to apply that as a negative force. When you're doing your force on node 5, that's a horizontal force acting to the right, so that is a positive force, okay? Positive forces are to the right and up. Negative forces are to the left and down, okay? So you're going to have a negative y, positive x. You don't need to do any unit conversions because it's in kips, and so since everything's in kips and inches, everything's all good there. So at this point, your model is ready to run. Like when you're ready to run, you're looking for all of the members being solid, you're looking for all your boundary conditions applied, and all of your loads applied. Actually, analyzing the structure is really easy. All you have to do is you have to run a first order elastic analysis. That's all, I mean, it's literally it, just first order elastics. Make sure that the option on the bottom says planar truss. If it says planar frame, your answers are going to be a little off, okay? But make sure it says planar truss. Yes, sir?
On the analysis, I've got two things that have a first order elastic option. They're static and time history. Which one?
Static.
Okay.
Static.
Thank you.
Time history is, so that's it. Let me say this. So time history, if we were trying to simulate like an earthquake,
Oh, okay.
that would be like doing that, like a vibratory analysis. Do you like my my sound effect?
I do.
Hyper technical, that sound effect. I'm a dork. I know, it's okay. If you've done it correctly, it should say applied load ratio equals 1, success complete. And so whenever you're doing a non-linear analysis, what it does is it increments the percentage of load, and for each little increment, it figures out equilibrium. So if the load ratio is 1, basically what it's saying is it was able to apply 100% of the load successfully, which is, that's what we want. So, all right. For post-processing the results, it's pretty straightforward. Pre-processing is creating a model, post-processing is viewing the results. We can do that a few different ways. We can create a report. So if you go to File, Create Report, you can say, give me all the internal member forces, give me all the displacements, and it'll just spit it out, which, by the way, is absolutely a brilliant option for your project, because MASTAN will create a report that spits it all into a nice little Excelable table, which Excel will be your friend on the project. You can also plot a diagram. So if you actually, this is what this structure looks like if you plot it. I think I did a scale factor of 40. Just so you're aware with deformation. So the way the scale factor works, what it does is, here's the thing. The real deflection right here, if you actually query the real displacement, it'll come out to be, I don't know, like 0.2 inches, 0.4 inches. I cannot visibly see 0.2 inches on a member that's 20 foot long. So that deformation scale factor, if it says a scale factor of 40, what it's doing is it's multiplying all your deformations by a factor of 40, so that when you look at the deformed shape, you can actually visually interpret it. That doesn't mean the structure is actually deforming that much. It's just so you can see it visually, okay? So that's our deflected shape. We can plot our deflected shape. We can plot our internal axial forces, report those, etc. Just so everybody's aware, we're going to pick up on this example on Friday. We'll have plenty of time if there's something that's a little fuzzy, but I'm going to stick around a little bit in case anybody has any questions. But that's all I've got, everybody. I will see you all on Friday.